Hey, this is Ana Doblas with the last video of the module Fourier Optics for the class Intro to Optics and Photonics. In today's class, we're gonna understand a little more how the lenses operate, and we're gonna define the transmittance of the lenses. I'm gonna show you two procedures to determine the complex amplitude distribution in a system versus one is going to be through the propagation, and then every time that we have a lens or a mask, we're going to multiply. But we also going to introduce the ABCD matrix and how to use it, how to estimate the complex amplitude distribution based on the ABCD matrix. So in a particular case, we're going to talk about the coherent 4F imaging system. We're going to show you how the lenses don't only perform imaging, but they also perform Fourier transforms. And we're going to understand a little more what is going to be the input response, the transfer function, and how we do spatial filtering in an optical system. All right, so let's talk a little bit about lenses, right? So let's assume that we have a plane wave, and we have said that we're going to have one. And then when we have a plane wave and we meet a converging lens, the light is going to converge to a point source. And when we have here a point source, means that we have a delta function. So always that we have a plane wave meeting a lens, we're going to have a point source in its back focal length. And then if we have a point source illuminating a lens, so from the point source, we have a diverging wavefront. And the point source is placed at the front focal plane of the lens, so that means at a distance d from the lens. At the end of the lens, we have a plane wave. So this means that if you have seen, we have talked about focal length at distance from back and front focal plane. So optical lenses are defined by a focal length that is going to be given by the parameter f. The other thing that we know is that optical lenses are defined by a f number. So the f number it's given is the focal length of the length divided the lens diameter. So this is going to be f divided, and then this is how we're going to define this is going to be our lens diameter, and then the f number provides a quantitative measure of the light passing through the lens. So if we think about our module number 1, where we were talking about ray optics, right? Here we were introduced that lenses were used to create images, right? So that means that here we have a point source, and then we're gonna have the image, the conjugated point source, and then here we have two conjugated. So from module 1, we know that 1 over C12 plus 1 over C23, that's equal to 1 over F, where C12, this is going to be the axial distance between the point source and the lens, and then C23 is the axial distance between the lens and the image or the conjugated point source. So in this class we're gonna show that lenses, they don't only perform images but they also do Fourier transform. But before talking about this, we need to define the transmittance of a lens, right? So we're gonna have exactly, we have what we have in front of the lens, you C1 minus, so well, if we start here from C equal to 0, that's gonna be our input. So at the input plane, C equal to 0, what we find it's a point source. So, and we say that a point source is gonna be our delta function. Now, what we have is just what we have right before the lens. So, right before the lens, what we have is the propagation of the light emitted of the point source propagated by a distance c. And here I'm using the Fresnel approximation that we derived in the previous class. Because we have a delta convolved with a function, we're just displacing the values. We are putting the x where it's centered, but the delta, the point source, it's centered. So we just not doing anything. So right before the lens, what we have is a diverging spherical wavefront. And if you see, we are dividing the plane wave with the quadratic X factor, so that means that we are under paraxial approximation. Alright, so now let's do what we have right after the lens. So right after the lens, what we're gonna have is what we had right before the lens multiply by the lens transmittance. Excuse me. So this is my lens transmittance. And my lens transmittance, what we have here is a converging spherical wavefront multiplied with a pupil mask. So this mask limits the size of the transmitting. Sorry about the letter. Let me try to type better. So the mask limits the size of the transmitted beam. So it's kind of adding some clipping effect, and this is my converging beam, or spherical, or paraboloidal. All right, so let's do the process together. So let's assume that we have a lens, right? And we have the front focal plane and the back focal plane, both of them separated by a distance f, right? And in the front focal plane, we have an object with transmittance t. We want to know what we have just right before the lens. So right before the lens, we have the propagation of the input plane with the kernel of the free propagation. So right after the lens, what we have is the information that we have right before the lens multiplied by the lens transmittance, right? And then if we want to know what we have at the back focal plane, so it's just the information that we have right after the lens convolved with the free space propagator at a distance f. And we just need, and if you see, we need to do a convolution of the propagation, then a product and another convolution. This is the whole process. Now I'm gonna show you how to do the. All right, so let's see this in a simplified method approach. So let's assume that you have any arbitrary system that you have described with the ABCD matrix, right? And you know the distribution in your input plane, and you want to estimate your complex amplitude distribution in your output. All right, so what you need to see is you need to pay attention to your B value and find out if B is equal than 0 or different than 0. If B is equal than 0, then your complex amplitude distribution is gonna be, and I'm gonna say here, like, your complex amplitude distribution is a scale replica of the input distribution. So that this one, so that means it's what we're gonna call is a geometrical image, where A is gonna tell us the lateral magnification. This factor right here, this is gonna be a spherical waveform that we're gonna have illuminated with a converging or diverging, but when we are getting intensity, this is gonna go away. All right, so if now the B is different than 0, so then we have a little more complicated formula. The formula tells us that we have a spherical waveform multiplying an integral, but if you see a little more the integral, so then we have here a spherical waveform with the curvature depend of A and B values, and within, so this whole integral, we can identify here the Fourier transform kernel. So this whole integral is gonna be the Fourier transform of the product of the input with a spherical waveform, which is gonna be at the end the convolution of the input spectrum scale with a quadratic phase factor has another quadratic phase factor. The Fourier transform of another quadratic phase factor also with the same scaling. All right, so let's see now. I really want to show you how lenses can make Fourier transform. So we have our input, it's our front focal plane, and we have a transmittance, and we want to see at the back focal plane, this is gonna be my output. And if you remember, when we do the ABC matrix, we always start from the back, like the last matrix is gonna be the first one, so this is gonna be the propagation from the input to the lens. This is gonna be my lens, And my first matrix is that's gonna be my propagation of the lens to output. So when we solve it, we see that B is equal than F, so that's gonna be if different than 0. So the output at the back focal plane, that's gonna be J over lambda B exponential of JKL0. Let me copy the formula, and now I'm going to talk what is L sub 0, because I put it on the slide, but I cannot ignore it a little bit on purpose. So now the input here is our transmittance JKA 2B alpha squared plus beta squared, the mixed term of the Fourier transform kernel. Alright, so L sub 0 is the geometrical distance between the input and the output plane. So in that case, it's gonna be 2F. D and H are equal to 0, so this goes to 1, and this whole X factor also go to 1. And now wherever we have B, we have F. So here we have a F. So the output is gonna be J lambda F, a global phase term due to the propagation. And then we have, if this spherical phase factor goes away, the integral is directly the Fourier transform of the input evaluated X over lambda F. So this is a proof that lenses can perform, and I'm gonna say real because it's in real time, Fourier transform. And when that was introduced to me as a student, I felt that this was the coolest thing ever, because I only was introduced to Fourier transform mathematically, but I never had an idea what it was until I went to this course about the fundamentals of diffraction, and then I started learning more about it. So what about the coherent 4F system? So the 4F system has two lenses. Originally, it's a 4F system because with the distance between the input and the output, it's 4F, so both lenses have the same focal length. So the object plane is at the front focal plane of L1 lens. So remember, FFP, this is gonna be front focal plane. And then the Fourier plane, this is at the back focal plane of L1 lens. That is the same as the front focal plane of L2 lens. So the lenses share the focal plane, and then the image plane is at the back focal plane of L2 lens. So BFP, this is gonna be back focal plane. So we don't know a lot of things at this point, but if here at the input I have a transmittance, right? I know that I'm gonna have right in front of the Fourier, or at the Fourier plane, I'm gonna have its Fourier transform. So that's gonna be X lambda F, Y lambda F. And now at the back here, what we're gonna have is we're gonna have the Fourier transform of what? Of my Fourier transform, right? So the Fourier transform of the Fourier transform, that's gonna be my new signal. We're gonna ignore some scaling here, but we're gonna have inverted, and it's gonna be lambda F u minus lambda fb. But this Fourier transform is gonna depend on the focal length and the wavelength, right? So at the end, what we're gonna have here is just the scale version of our transmittance. And that is how we're gonna now verify this intuition. So let's do the ABC matrix, and remember that we start from the end to the beginning. So we have the propagation from L2 to the output, then which is gonna be a distance f. Then we have our length L2. We have the propagation for the Fourier plane to L2, and then the propagation for L1 to the Fourier plane, which is the same, just doing the free propagation from L1 to L2. That's why we have here the 2f. Then we meet with our length L1, and then we have the last propagation from the input, the object plane, to the L1, which is here our last propagation. And when we multiply all the metrics, we found out that A and these are the same and is equal to -1, and B and C are the same and equal than 0. So since B is equal than 0, now my output is gonna be 1 over A jk L sub 0 jk C over 2A x squared plus y squared, and now the scale input, right? So L sub 0 is the geometrical distance, so this is gonna be for f. C is equal to 0, so this factor it's 1, and now A it's -1. So my output negative jk for f, and then f of minus x minus y. So this term right here, this is a global phase due to the propagation. And this term right here, this is my inverted input distribution. But if you see, we have same scale between the input and the output plane. So if we are thinking about our intensity, this global phase is irrelevant. So in terms of the intensity, we're gonna share the same distribution. The intensity of the input is gonna be the same, but just inverted. So in a general case, we don't call it strictly Fourier system, means that the two lenses, they have the same focal length, but we also call them Fourier systems those ones that there are two converging lenses but they have different focal length. So if we work the matrix, so we have the propagation from the second lens to the image plane, the lens, the second lens, then the propagation for the Fourier plane to the second lens, the propagation from the lens 1 to the Fourier plane, the matrix, the lens 1, and then the propagation from the object plane to L1. So when we work out the matrix, we find out here that A and D are equal to, well, A is equal to the inverse of this, so it's going to be minus F2 over f1. This is what we call a lot of time our lateral magnification. And b is equal to c, that equal to 0. So the difference here is now there is a scaling factor. So the output, yes, it's gonna be equal to the inverted input, but not at the same scaling factor. So it's gonna be a scale replica of the inverted input. And now our global phase term is not gonna be anymore for f, it's gonna be 2f1 plus f2. But the idea is the same, that the output is an inverted replica of the input. So let's complicate a little more. So we are assuming that we have ideal systems where we don't have any crop of the spatial frequencies of the input. But in a realistic way, in the Fourier plane, we're gonna have a mask that is gonna crop the spatial frequencies of our object, right? So, and remember that we need to do the step right before the Fourier plane. So right before the Fourier plane, what we have here, and I'm ignoring some constant first term, but we have here is the Fourier transform of our input, the scale Fourier transform of our input, and now what we have right after the Fourier plane. So right after the Fourier plane, what we're gonna have is, and again I'm gonna do proportional because we're gonna ignore some constant terms and a spherical waveform. We just want to see the role, so that we have this convolve with our mask. So remember here that we are introducing a mask. And at the image plane, we have the Fourier transform of the information that we have right after the Fourier plane, evaluating at x. U is gonna be x over f lambda f2, and then b is gonna be y over lambda f2. So here we're gonna have, I'm showing here that because you have that scaling on the Fourier transform, that's gonna have some scaling there, but the Fourier transform of the Fourier transform becomes the transmittance with a minus lambda f1 u minus lambda f1 b, and now that convolution becomes a product. Sorry, this is not convolve, this is a product. So this product becomes a convolution of the Fourier transform uv. And now we need to put uv between x over lambda f2 and b y over lambda f2. So I'm gonna put it right here. So our output is minus x f2 over f1 minus y f2 over f1 convolve with the scale replica of the Fourier transform of our mask, where the scaling depends on f2, but then the scaling of the input depends on both focal length. So this means that if we are considering that we have a linear simple invariant system, right, where we have that our output is equal to our input convolve with the input response, that means that our input response are h xy. That's gonna be the Fourier transform, the scale version of the Fourier transform of the mask. So scale replica of the mask Fourier transform. And then our transfer function, our capital H, which we know that is the Fourier transform of the input response. That's gonna be a scale replica this is gonna be a scale replica of the mask, the inverted mask. Considering that our mask is a circle, we reduce r sub 0, and r is defined by our radial coordinates. So then its Fourier transform is where we call our disk function. So this is like the Mexican hat, where again we are defining everything with the radial coordinates in the frequency. So if we have, for the coherent version, we have our input response is given by our disk function, a scale version of the disk, right? But then for the incoherent version, and we can talk more in a intro to Fourier optics class, but basically it's gonna be the square modulus, the absolute modulus square of the coherent input response, and that's gonna be our disk square. So how it looks like, the airy disk looks like concentric rings of decreasing intensity. And this is where it's gonna be our point spread function, which is the input response for the coherent, incoherent light. So if you can draw some profile of your disk in terms of your radial coordinates. So here is your disk square, right? And what you're gonna have is your concentric rings, where every time you have less intensity, and the main lobe contains around the 70%, and the first minimum is for a 0.61 lambda f2 over r sub 0. So this is what AB defined as the resolution limit. They say that the minimum distance that we can solve is defined when we are in the first minimum. And you see that if the radius of your mask increases, then the minimum distance gets reduced, so that's gonna be better resolution. So that we increase our radius on the mask makes like a wider mask, so we can capture more spatial frequencies of the object. And remember, R is defined as the minimum distance in which two separate point sources can be distinguished. So I want you to think about, and this is a really important point to finish the class, is what is the mask doing for us, right? So when we have object, mask, and image, we know that the image is the convolution of the object, a scale version of the object. We might have some scaling here, but with the Fourier transform of the mask with some scaling, right? So you have this convolution, so that means that you're gonna have blur, a blurring effect. That means that you are losing of the high spatial frequencies. But what about if now your mask is not like a low pass filter? This is gonna be like a low pass filter. What about if your mask is a passband filter? Or it's a high pass filter? Then what you're gonna do, you're gonna use it, you're gonna be able to do some edge detection. So you're gonna use the contour of the object, but we can also do other type of filtering. So let's assume that you have a sign along the X and the Y direction. So this is gonna be my sign, my vertical sign, the Fourier transform, and this is gonna be wrong color choice, sorry. And this is gonna be the unit impulses of my sign along the horizontal, right? So we here are only allowing the horizontal fringes, so we are losing, oh, let me change the color here. So here we are lost the vertical sign, sinusoid. But backward, when we are doing, we are shifting our filter. So let's assume that you have a slit on a rotational state and you can rotate it. Now if we orient it on the for the vertical deltas, then here what we are losing is our horizontal sinusoid. So it's not only cool that we know that we do Fourier transform and the lenses make images, but we know how to control the magnification, because it's related with the ratio of the focal length between the two lenses in a forest system. But also now that we know where is the plane, the Fourier plane, we can do some fancy spatial filtering to get our final result. I hope that this class encourages you. Fourier optics means a lot to me. Thank you.